All right. Hello, everyone. Welcome back. Sorry about that last minute cancellation of class. When things happen. And unfortunately, there's going to be a few complications today. I'm going to have to mute the stream for 1 to 3 minutes in about an hour for something going on. And then after that, I'm actually going to have to close out class about 15 minutes early. I have an appointment immediately after related to class being canceled last time. So I have to go get that taken care of. But besides that, let us soldier on. I'm sorry we had to lose that time. If I had been able to record, a little far ahead there because I was looking at where we were going today. If I had been able to record something so we didn't lose the time, I would have, but I just haven't been up to it. So all the due dates we'll pull back up at the end. But nothing has changed. We'll just put in due dates for where we're going to start today, which is 3.2. So hopefully you've been staying on top of all your homework, my MyMathLab stuff, the Excel stuff, and then I will have a quiz. I think maybe 1 or 2 classes ago I said I was going to have a quiz ready, and then I never said anything in class about it, so I didn't post it. I don't like posting things unless I give you the details in the lecture. I don't think that would be fair. So I did hold off on giving you 1 quiz, and the quiz that I give you today, I'm actually going to decide on the fly whether it's going to be that one or I'm just going to skip it and give you the next one, but we'll know that by the end. And before we actually get into 3.2, I want to go back to the guided worksheets and just do a couple from the next activity. The last things we did were problem number 2, all these conversions, and I left some of them to your discussion boards, which I have not gone in to talk about yet, but we'll do that. I don't know if I can say today, because between my appointment and having to teach my second class later in the afternoon because of that to record it, I might not be able to get to it today. If not, it'll be tomorrow. But anyways, I know I still need to give you some of these answers as promised. So I just want to do 1 or 2 more of these dimensional analysis type problems versus the proportion style before we move on to the next section. Now remember that everything in these sections is pretty heavily related. It's not always just doing the same thing over and over and over, but we're always in the same ballpark of what we're talking about. Proportions, ratios, dimensional analysis, they're all very, very tied together. I'm not saying that we're doing the exact same thing if it's a proportion or if it's dimensional analysis or if it's a ratio. I'm just saying that they're all heavily related, and a lot of them can be, turn into this idea of a proportion, fraction equal to fraction. So what this activity does is it kind of focuses on showing the work as a proportion and showing the work as dimensional analysis and showing that the answer is the same. Now, we've done this once or twice already, so I'm not going to do all of these. I might assign some as group work. You'll find out soon enough. But the first example has been done for us. They said, all right, we want to convert 10 inches to centimeters using the conversion that 1 inch is 2.54 centimeters. So they say, okay, well, if you want to do as a proportion, you would write inches over centimeters. Now, they always like to write their units in this initially, but then when they cross multiply, they get rid of them. I think that's kind of weird. So me personally, when I'm setting up a proportion, it's the only time I don't write the units. So let me show you what I mean. This is the way I would be doing. Where's my Zoom stuff? This is weird. All right, thank you, Andrew, because you just made me realize why I couldn't write on my screen. I didn't hit share screen. So I'm just gonna say I've been sick, so we'll chalk it up to that. Oh boy, sorry about that. If I didn't have to, I probably wouldn't be teaching today, but I can't have y'all be missing a week. All right, so Working with the best we got. All right, so we got 10 inches, and we wanted to convert that to centimeters, and we know that 1 inch is 2.54 centimeters. So the way I would have done this is just slightly different than what they have in this box. Again, I'm showing my version of this. I would have wrote inches over centimeters, and then, then I would have made my fraction equal to a fraction. One of these sides need to be the conversion. So 1 inch is 2.54 centimeters, this right here. And it doesn't matter whether it's the left or right side. So 1 is 2.54. I got the inches in the top, centimeters in the bottom, just like it says. And on the left side, we're supposed to be converting 10 inches. Now, since that's an inch, we put it in the top. We don't know how many centimeters it is, so there's an X, and then you'd cross multiply. This is the difference of the way I set things up versus them. When I do proportions, I label the units to the side, which ones are in top, which ones are in bottom. And that way, when I solve for X, I know since it's in the bottom, it would be in centimeters. They write the units in it, but then when they cross multiply, they don't write them. This is really weird. I don't like that they choose to write the units in one version, but not in another, which is why I just do it this way. Again, labeling that anything in the top is an inch, anything in the bottom is a centimeter. So I know, oh, that's 10 inches. I know this is 2.54 centimeters. I know this is 1 inch. Now, if I was doing dimensional analysis, I would absolutely do it the way they have on the right. So the left side is the proportion setup, which when you cross multiply, you get 10 times 2.54, which is 25.4, is equal to X times 1, which is X. So that says X is 25.4 centimeters. Why do I know it's centimeters? Because the X was in the bottom, centimeters are in the bottom. The other way, this is exactly how I would have done it. I would have, if I wanted to do dimensional analysis, which is my preferred way personally, but you can do it however you like. You start out by just writing the 10 inches, and you have to have the units with dimensional analysis. That's what dimensional analysis is centered around. And then you multiply by your fraction, that's your conversion. The 1 inch is 2.54 centimeters, but you have to out with the old, in with the new. Old units go on the bottom. Inches are the old, so the inches go on the bottom. Then put the rest of the numbers and units in place. 1 inch is 2.54 centimeters. The inches then cancel, and 10 times 2.54 is 25.4. You get your centimeters. Everything is all good. So once again, when you're doing homework, when you're doing quizzes, when you're doing tests, I don't care which way you convert your units. I need you to be a master, an absolute master of one of these types. If you never do it as a proportion, if you always do it as dimensional analysis and you always get it right, wonderful. Or vice versa. I don't care how you get things done. I care that you have a way that gets things done that makes sense, that always works. Always how I roll in class. Okay, so I got to clear my screen so we can actually get to the problems, which are only going to do 1 or 2, since we're doing 2 methods. And the first one is converting 82 feet to meters by using the fact that 3.281 feet is a meter. Remember, in a test, I will give you all conversions except time. So if you look at number 2 below, convert 3 days to minutes using these, I would not give you any of this information on a test. Never, ever, ever. You better know that 24 hours is a day, 60 minutes is an hour, 60 seconds is a minute, and 365 days is a year. They also don't give me enough space to write for that one, but we'll cross that bridge when we get there. Number 1, converting 82 feet to meters. So let's pop the annotate on. Let me get a color that'll go in the box. Let's go with red. So the left side we're going to do as a proportion. The right side we will do as dimensional analysis. So for the proportion, we're converting between feet and meters, and they gave us the units to go between feet and meters. It doesn't matter whether I write feet on top or meters on top. I'll write feet on top because it's the first thing I see. So feet over meters. So by doing so, when I set my fraction equal to a fraction, any unit in the top has to be a feet, any unit in the bottom has to be a meter. We had 82 feet, so I'll put the 82 in the top. We don't know how many meters it is, that's the unknown, that's our X. And then this 3.281 feet to 1 meter, that goes in here, top and bottom, specifically 1 meter, meters go on the bottom. 3.281 feet, they go on the top. How do I know that? Because I told myself right here what's going where. You could write this thing completely upside down. You could swap the left and the right sides. There's 8/16 ways to write it and get the right answer. You'll cross multiply, and you'll get 82 times 1 is 82. And then the 3.281x, the 82 times 1 is the 82, as we said. That's 3.281x. You'll then have to divide both sides by the 3.281. And let me get my calculator, which I can't put on screen, as you already know in this format, unfortunately. 82 divided by 3.281. You'll get 24.99, and we're rounding to the nearest tenth, one decimal place accuracy, they said. So that 24.99 is going to round to 25. 25 is equal to x. The x that was in the bottom originally, so those are meters. So it's 25 meters. Here we go. The dimensional analysis version instead, though, we start with our 82 feet. And we're going to multiply by a fraction to out with the old and in with the new. The old units are the feet. So before I even look at any of the conversion mess, I know I can go ahead and write feet in the bottom because I need those gone. But specifically, 3.281 feet is 1 meter, and we're converting to meters. So the new units go in the top, the new. I may have said moo there, not the Greek letter, not the cow, new. And it's 1 meter is 3.281. Don't rush, pay attention, take your time, so your feet cancel. You're doing 82 divided by 3.281, which we already know is 25. The feet cancel, the units that we see left over are the meters, and we get the same answer. It works either way. Now with number 2, I'm going to have to do the work to the side over here for the proportion version, because there's going to need to be 2 proportions. They did not put enough space here. Shame on the textbook company. Excuse me. So on your own paper, if you actually have these printed, just find some space somewhere to the side, write small, whatever you have to do. We're going from days to minutes, but we don't know how many days are how many minutes. We know how many days are hours, and we know how many hours are minutes. So this is going to be a double setup. For the first one, we're going from days. Well, what can we go between? Days and hours. So we're going to go days over hours. So we're starting out with 3 days. 3 days, that goes in the top. So 3 over something equals something over something. We don't know how many hours 3 days is at the moment, so that's our x. But we do know that 24 hours is a day. So 1 day is 24 hours. Cross multiply, you'll get 3 times 24 equals x times 1. 3 times 24 is 72, so 72 is equal to x, which it's 72. Since the x is in the bottom, it has to be hours. Does that make sense? Yes, it does. If one day, excuse me, if one day is 24 hours, then 3 days would have to be more than 24 hours. Now we're going to have to go from hours to minutes. We know how many hours are how many minutes. It's right here. So we're going to go hours to minutes. That blue is kind of hard to read. Let me switch back to white. I always forget that. Hours to minutes. Fraction, equal, fraction. If you wanted to go minutes over hours instead, that's fine. If you want to have your left fraction be my right fraction, that's fine. All right, well, we're at 72 hours. So 72 is what goes in the hour spot. We don't know how many minutes that is, so that's an x. But we know how many hours to how many minutes. It's 1 hour to 60 minutes. 1 hour, 60 minutes. You'll cross multiply. So we take the 72 times the 60 is equal to the x times the 1. That's going to be 4,320 is equal to x. X was in the bottom, so it's a minutes. So it's 4,320 minutes. So that was doing it as a proportion. on the right, and again, I don't really have enough space here. You know what? I can make this work. I'm just going to act like this part's a fraction bar or something. I'm going to make it work. So doing it as dimensional analysis, DA, dimensional analysis, we start out with our 3 days. We multiply by a fraction. Out with the old, in with the new. That's the whole point of dimensional analysis. Out with the old, in with the new. Out with the old means the old goes in opposite spots. Now remember, we could have the original units in the bottom, so then they go on the top of our multiplier. Pay attention. We saw that last time. So we know days go on the bottom. We can't go straight from days to minutes. There's no conversion. We can go from days to hours. So days to hours. How many days to how many hours? 1 day to 24 hours. And that will cancel the days and leave everything in hours. But we need to be in minutes. So we need to multiply by another fraction to go from hours to minutes. So this fraction, we're going to go from hours to minutes. Out with the old. Hours are originally at the top, so they go on the bottom, which means the minutes go on the top. And we know 1 hour is 60 minutes. So the hours cancel. The only units left over will be the minutes. And then we just multiply the 3, the 24, which is 72, and 72 times 60, which is 43, 20 minutes, the same answer. That's a check mark right there. Okay, so for the discussion board, you're going to do 3 and 4. So D and B, and there's 4 opportunities here. There's 4 opportunities because question 3 has 2 parts. So one student can come in and convert 250 rubles to dollars using the fact that 1340 rubles is $20. You know, several years ago when this was created. It's probably not the same now. So one student can take this doing it as a proportion. One student can take this using it as doing it as dimensional analysis. So we'll have 2 students be able to work on number 3, and then 2 students be able to work on number 4, going from 120 pounds to kilograms using the fact that 1 kilogram is 2.2 pounds. So one student, ooh, what happened with my pen there? So one student can do the proportion version, and then one student can do the dimensional analysis version. I'm going to skip number 5 because it's a bigger one and it's not on the screen, and I don't want to have to erase, scroll and write and scroll and write and scroll. This is good enough. So this is 4 opportunities. So again, this will be discussion board. Number 3 and 4, that's 4 opportunities. Please, as a student, do not take more than one of these. Only take one of these 4 opportunities. Now, if someone comes in and does it wrong, that will always open up another student to be able to swoop in and take an opportunity. If you think someone's done it wrong and you post it, now maybe you're the one that's wrong. I'm not, because you never know, that can happen. It's certainly happened in my life, but that's still an opportunity. If you think someone is wrong, whether they're wrong or even if they're right, if you come in and say something, that still counts as an opportunity. But I don't want to have 2 students come in and do the exact same problem twice with the exact same work. Now, what you might think if you're clever is like, oh, well, I'm just going to say that they're wrong, even though I know they're right. And I'm just going to show some bad math. Please don't do that. Please have constructive arguments and discussions. Because if you fudge some numbers, you might end up leading someone to believe that they're right when you were intentionally wrong, if you know what I'm saying. I'm trying to just kind of relate this to what happens in the real world. People in the real world fudge numbers constantly, and then people blindly believe them because, oh, I see that they wrote this down. They said they're right, so they're right. No. Use your own thoughts. Make educated decisions, all that good stuff. All right. So I got it clear now. Let's take off annotate. Now we can get into 3.2 officially. Which you will see I have very, very, very little typed up in the notes to share. That's because 3.2 is a fairly short section. 3.2 is on scales. Scales are literally a proportion. Scales are literally a proportion. Everything that's a scale is a proportion. Look, scale, you can set these up as a proportion. Scales, one of what our textbook likes to use for scales is they like to talk about models. They tend to like to talk about model airplanes and model cars. It doesn't have to be just cars and planes. You could also have model trains. And a model, when you talk about a car or a train or a plane, as long as they're built appropriately, they are proportionally built on a smaller scale. So let's say you have a car that's normally, I don't know, maybe 10 feet long, maybe 15 feet long. Let's say 15 feet long. So we got a pretty long car from the 70s, 15 feet long. But you want to have a little toy for your kid, and your kid really likes your 1970s 15-foot long car, Oldsmobile, whatever the heck it is, banana boat, I don't know. We had a quote banana boat growing up, a yellow Oldsmobile, and we called it the banana boat. So that's the joke there. So your kid really likes your 1972 banana boat Oldsmobile and wants a little model car of it. So you go to the store and you find one, and that little car is built proportionally so that the length of the hood is scaled to the length of, say, a tire, to the length of the mirror, to, you know, the width of the car. It's just a shrunk down version of the real life car. So everything is built like if you had a person small enough to fit into it, that person would basically have the exact same scope of the car. And models don't have to be just movable objects like planes, trains, and automobiles. You know, good movie from the 80s right there. It can be anything. You could have a scaled figurine of a person or a dog, or you can talk about scaling the planets in our solar system to a much smaller scale for you to build a model for class or something like that, whether it's, you know, something you can bring in physically in the palm of your hand, or, you know, holding it with 2 arms, or maybe you do it out on the quad of TCC or something like that, which is going to be relevant for what we're about to talk about. So anyways, my rambling aside about how a scale is a proportion and how we can relate to it, typically the first quantity is scaled to 1 when we're calling the first quantity the model. So when we're talking about scales, we generally write them as model over actual. It doesn't have to be that way. It could be actual over model, but then the sentence that I have highlighted, we would then change it to the second quantity is scaled to 1. So something, instead of saying typically the first quantity is scaled to 1, a slightly better way of saying this is typically the model is scaled to 1. Because we want the model to be 1 inch or 1 meter or 1 foot, a nice 1 value, because it gives us a way of having a K found very easily, just multiplying, say, the number of inches the real thing is to the model, multiplying that by the size of what you want, and boom, you get a nice y equals kx set up instead. So the actual size of something would just be 72 times the model. So if your model is 1 inch long, then the actual distance of that, the length of it, would be 72 inches, 72 times 1. If your model is 1 foot long, then the actual object would be 72 feet. If your model was 1 mile long, maybe you have a really, really, really giant model of something, that means the actual would be 72 miles long. So again, there's nothing new about this. It's proportions, it's fraction equal to fraction. We typically are scaling something to 1. We have dealt with this quite often. In the past, we typically had been scaling the second thing to 1, but now if you're going model over actual instead of actual over 1, you're and I misspelled that up here, modal. What did I do? Oh, no, I didn't. Why did I think I misspelled that? I thought I had an A and I didn't. I'm telling you, guys, I don't feel perfect today, guys and girls. Sorry. All right. Where was I? I got sidetracked. So again, proportion, you'll have the scaling factor. You have to be given the scaling factor. or it has to be something that you would measure in, say, a lab setting, or, you know, where, and by lab setting, I mean just you in the real world. So if you had a model, say Mustang in front of you, and then you had an actual Mustang in front of you, you could measure the length of the model, you could measure the length of the Mustang, and you would have your scaling factor. And then you could find the length of anything on the model or actual based on the other. Okay, so let us go to the guided activity on page 126. Zoom in a little. Yeah, taped red. Okay. So you wish to create a scale model of the solar system, and again, this is page 126, on your campus quad that is circular and measures 240 yards in diameter. So our campus quad, not TCC, but this particular campus is circular and measures 240 yards in diameter. So diameter is the distance from end to end. I'm gonna erase this in a minute, but assume that I just drew a perfect circle, not the band. Then this distance right here from end to end would be 240 yards. From here to here. That's what diameter is. Circumference is the distance around. So this is our quad. It's kind of weird to have a circular quad. I'm sure they exist in some schools. But either way, we're just pretending. This is the TCC quad. It's 240 yards wide. Honestly, for the sake of this problem, it doesn't really matter. But I will bring up something about it in the end. So there's our quad. And inside of this circle, we want to have our sun here, and then we want to have Mercury here, and then we want to have Venus here, and then we want to have Earth here, and then we want to have Mars here, and Jupiter here, and their planets are getting bigger, and you get the idea. And they don't have to necessarily be straight out in a line, but their radial distances are supposed to be proportional to how they are in the real world. So if all the planets were aligned in the universe like this, we know the distance from Mercury to the sun is, say, well, 57.9 million kilometers. So this distance in reality is 57.9 kilometers. Then from Venus to the sun, it's 108.2 million kilometers. From Earth to the sun, it's 149.6 million kilometers, et cetera, et cetera, et cetera. Whether they are lined up like this or not. So again, if Venus was here, that distance is still the 108. If Earth was here, that distance is still the 149. But we want to have this on our quad. We can't have Mercury be 57.9 million kilometers away from the sun because the quad's only 240 yards. 240 yards is much, much, much less than 57.9 million kilometers by an immeasurable amount, practically. So what we want to do is, we want to set the distance from the sun to Mercury as 1 yard. So on our model, so here's our quad. I'm just gonna do the sun as a dot now. Here's our sun. If here is Mercury, this distance right here on the quad is supposed to be 1 yard. Then we want to have the distance to Venus be proportional, so it's scaled appropriately. Now, Venus is further away than Mercury, so this number should be bigger than 1. I'm going to erase these things in a minute, but this number should be bigger than 1. That says greater than 1, because Venus is further away. Now, Venus's distance was about 108. Let's just call that 100. Mercury's was about 50. Venus is about twice as far away. So if Mercury's 1, if you do the whole doesn't make sense, this answer should be about 2. Earth, that's 50, 100, 150. This should be in the ballpark of 3. This should be in the ballpark of 4, maybe 5, maybe 4.5. So you can get a better sense of scale of where these things are. So if I got an answer for Venus to say 500,000, I know that's wrong because it should be proportional. It should be close to 2. All right. So I need the space for work. So we are scaling Mercury to 1 yard. That's our model. So the model length from the sun to Mercury is 1 yard. What is the model scale we're using? Well, the 1 yard now used to be 57.9 million kilometers. That's the scale. We're saying that 1 yard in the model is 57.9 million kilometers in the actual. This is model to actual. That's the ratio between the model length and the actual length. So they say to use this ratio to determine how far the other planets would be and fill in the table to 2 decimals of accuracy. So I'm only going to do a couple of these. And then I want y'all to fill in the rest, guess where? In the discussion board. So I had 4, I'm going to leave maybe 5 of these, maybe a few more. So the easiest one to tackle next would be Venus. So let's do this one. So 57.9 is to 1 as 108.2 is to, well, this is our x for now. I'm going to use v for Venus, so I'll call this v when I'm setting up the proportion. So we're going to go model over actual instead of actual over model. You can go actual over model, there's nothing wrong with that, but this is just how we say to write it. That way you scale the model to 1, the first one. So fraction equal fraction. So the model length, model over actual. So we need to compare Mercury to Venus. So the first fraction I'm going to have be Mercury, and the second one I'm going to have be Venus. If you want to do Venus then Mercury, that's fine. If you want to go actual over model, that's fine. Just be consistent. So for Mercury, its model length was the 1 yard, and its actual length was the 57.9. Now these actuals are in millions of kilometers, so just make sure that if you are finding an x there, that the answer is in millions of kilometers. Venus, well, its actual was the 108.2. We don't know its model length, so that's where I'm writing v for Venus. So we're going to cross multiply this. Cm for cross multiply. You get 108. Oops, what happened there? 108.2 is equal to 57.9 V. The 108.2 times 1, I just went ahead and wrote that as 108.2. You're going to divide both sides by the 57.9. Which will tell us 108.2 divided by 57.9 is going to be 1.87 when rounded to the nearest tenth. 1.87. That's our V, that's the model. It's 1.87. So 1.87 yards, does that make sense? Yes, it's about 2. Venus was about twice the distance to the sun from Mercury, so its model should be about twice the distance Mercury was to the sun. So for the Earth, again, always going model over actual, I'm just going to be consistent this whole time. For Earth, so we'll go Mercury to Earth. So we got fraction equal to a fraction, model over actual. For Mercury, that's the model was the 1, the actual was the 57.9. For the Earth, we're going 149.6 is the actual, 149.6. The model length is unknown, so I'm labeling it E for Earth. Now you might say, Mr. Beckner, why did you use Mercury and compare it to Earth? Why didn't you compare Venus to Earth? Guess what? You could have. This is just a proportion table. That's exactly what we're doing here. The first one, here is me drawing a box around 4 numbers, corner, corner, corner with 3 of those numbers, an unknown, boom, there we go. Here is me drawing another box with the corners having number, 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 so 3 numbers, and then an unknown, that's our X. So we just skip that row. Does that mean I have to do it that way? No, I most certainly could have drawn the box this way, that proportion box, and then you've got number, 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 and then you're just doing Venus to Earth. But why did I choose Mercury? Because there's no borrowed information in Mercury. I rounded to get this answer for Venus. So if I use this rounded answer to get Earth, that means Earth is going to be a little off. And then if I use that to get Mars, that means Mars is going to be a little off. And then each one is going to be a little worse off because we keep using borrowed information. We keep using rounded information. these numbers will not be terrible. They just, if the answer is supposed to be like a 0.7, you might end up with a 0.6. That's all that really happens there. If you use Venus to Earth and then Earth to Mars, et cetera, et cetera. Okay, so when we cross multiply, you're going to get 149.6 is equal to 57.9 E. You're going to divide both sides by the 57.9. And then you should get an answer in the ballpark of 3. 149.6 divided by 57.9, which is 2.58 rounded to the nearest tenth, 2.58. That's our Earth model distance. And that's in the ballpark of 3. I mean, it's 2.5. It's not super close to 3, but again, we were just spitballing numbers. The point of saying it's close to 3 is if I got an answer of 200, that ain't close to 3. If I got an answer of 0.7, that's not close to 3. All right, so I'm going to skip Mars. I'm going to skip the asteroids. I'm going to skip Jupiter. I'm going to skip Saturn, Uranus, Neptune, and Pluto. I'm sorry, I'm going to go straight to Pluto. So P for Pluto. So again, model over actual. I'm going to compare Mercury to Pluto. Fraction, equal, fraction. So this is the box I'm drawing, if you like drawing those boxes every time. Number, 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 unknown. So for Mercury, the model was 1, the actual is 57.9. For Pluto, the model is unknown. That's our variable P for Pluto. And then the actual is the 5915.8. That's 57 compared to 5900. Those are off by about a factor of 100. So this answer should be in the ballpark of 100. Cross multiply, you get 5915.8 is equal to 57.9p. You're going to divide both sides by the 57.9. If you're someone who's good with pattern recognition, you'll see that each of these times you're just taking the planet distance and dividing it by Mercury's distance. That's all you end up having to do. It's pretty consistent. And then when you do that division, you should get 102.17. So 102, sorry for the change in color, but that's about 100. That's pretty good. So for your discussion board, you want to find those 6. So that's now 10 opportunities, and that's if no one even feels the need to correct anybody. So you're going to do Mars, and then the asteroids. There's a big, giant asteroid belt between Mars and Jupiter, and they just say the distance is that. So you're going to do Mars, asteroids, Jupiter, Saturn, Uranus, and Neptune. So that's 6 of them. So Mars through Neptune. Okay. How are we on time? 9:10. We're not going to do that one. This next exercise, this is one I usually do, but I'm trimming in particular because we just lost a class. This, if you could jump like a frog activity on page 127, 128. I'm not making it a discussion board. I'm just saying that maybe put your eyes on it and see what you can come up with on your own. But this is talking about unitless scales. This is kind of like when you're comparing something to itself or something that's too similar and has the same units. So with most of our scales, with most of our models, most of the time, notice I keep saying the word most, typically you're going from like inches to meters or feet to miles or something like that. You're changing units. So that's a united scale. That's when in dimensional analysis, you're multiplying by an old and a new and canceling the old, all that stuff. Not all conversions change units though. So this in particular, they're talking about a 3-inch long frog can jump 60 inches. Now I'm assuming they mean 60 inches horizontally and not vertically, because there is a difference there. But maybe they are saying vertically. I'm assuming horizontally. I'm not a frog expert. But when I ask myself, does it make sense? That number makes more sense for a horizontal jumping distance than a vertical jumping distance. I just don't see a lot of frogs jumping 5 feet in the air, but I can certainly see a frog hop along horizontally pretty quick. So they start talking about all this. Is this a unitless ratio? And the answer there is yes. And that's because these are the same units, inches to inches. So when they say to do what is the ratio between body length and jump distance, you're going 3 inches over 60 inches. I'm just going to show you the basic idea. 3 inches over 60 inches. And the units cancel, and you get 1 over 20. And you end up with this unitless scale. Now, does that complicate things? Honestly, not really. It just means you can't use the idea of out with the old and with the new. You really have to make sure that if you said, okay, well, now I want to assume that a human being can jump the same distance as a frog, proportionally speaking, down here, C, assume that the jump distance is proportional to body length, find an equation for this relationship. Well, up here, this was the body length, and this was the jump length. So when you go and try and make a proportion for this, you just say body over jump is equal to 1 over 20. For every 1 inch of body, that means you can jump 20 inches. So for every 1 inch in body means you can jump 20 inches. So if you were 2 inches in length, then that means that you could jump 40 inches. If you have a body that's, say, 4 feet in length, that means you could jump 80 feet. Notice I just switched units there. That's one of the benefits of a unitless scaling quantity, is the units don't matter. You don't have to think about out with the old and in with the new. You can just change the units on the fly. So that's the point of this activity that they try and emphasize. But again, I'm not going to do the whole thing because we don't have time. We've got to trim the fat somewhere. Okay. 3.3, rates. Rates are a ratio. Notice the similarity of those words, and we've pointed this out before as well. We definitely have. Rates are a ratio. Rates are a ratio of 2 different types of quantities, though. So that thing we were just doing with the frog, we were saying for every 1 inch of body length, it can jump 20 inches. So if you have a human that's 5 feet tall and you assume that it can jump like a frog, that means it could jump 100 feet. Clearly, that's a poor assumption. But anyways, those were a scale that were unitless. So you can still call it a ratio because it's a fraction of 2 things, but we don't really like to call it a rate. Rates, and we don't like to call that frog problem a rate, is because it was going from inches to inches or from feet to feet. They were the same type of quantity. Rates, we typically say, are 2 different types of quantities, like comparing apples to oranges, just that plain Jane boring statement, which basically just means thing 1 to thing 2, or students to teachers, or distance to time, or miles to hours, or feet to second. And those last 3, I only have 2 of them typed, but the last 3 things I said, distance to time, miles to hour, meters to second, they're all the same thing, just labeled differently. One's labeled with dimensions, and one is labeled with the quantity type, that it's a distance. So if you want to talk about your speed, you could say, all right, well, that's comparing miles to hours, or you could say you're just comparing a general distance to a general time. Or if you're not using miles per hours, maybe you're using feet per second, then you could write feet over seconds. Please remember that the word per means that the next thing comes in the bottom. That is something you never ever get to forget for the rest of your life, being experts on quantitative reasoning after this course, right? Right. When you have the word per, that means the next unit goes in a bottom. That's going to be a critical skill to understand and have moving forward. I mentioned that cost analysis can be as simple as a rate. Oh man, this right here. This is one of my favorite things in the whole world, cost analysis. You go to the grocery store or whatever store, and you're comparing two different things, and maybe they're not the same size. So you've got a bag of, I don't know, a bag of chocolates that's a pound, and it costs $2, and then you see another pound of chocolates that's a pound, I'm sorry, another pound. Let me start over. You see 1 pound of chocolates that's $2, and then you see another bag that's 1.5 pounds, and it's $3.20. And you go, well, which one do I buy? And you might say, well, I'm going to buy the one that's $2 because $2 is less than $3.20. Okay, if all you have in your pocket is, say, $2.50 or something like that, then absolutely buy the $2 item because that's all you can afford in the moment, unfortunately. But if you're trying to think about long-term savings, maybe you're going to keep buying this thing over and over and over and over and over, or maybe you're just a thrifty spender all the time anyways, no matter what angle you're approaching this from. What you want to look at is cost analysis. Look at the cost per item, or the cost per ounce, or the cost per pound, or the cost per M&M, or whatever it is you're talking about. You need to look at it on a smaller scale as a rate, and then whichever one is a smaller value, that's the better buy when you think in the long run. I'm trying to decide if I want to do that first. You know what? I'm already talking about it, so yes. I usually save the cost analysis for a little later in this section, but let's go ahead and do it now. So let's go ahead and talk about what cost analysis looks like. It can be as simple as a rate. And again, you want to look at the cost over, what in the world? There we go. Cost over something else. Maybe it's the weight, maybe it's the number of items. So in this denominator, I'm just going to write multiple options. Maybe it's based on, maybe you're choosing to do it based on weight. Maybe you're choosing to do it on the number of things. There's a few different ways you can do this. That's why I have another slash and an etc. But you're always taking the cost and dividing it by something. And you want this to be small. You want to have the smallest cost per. Think about it this way. If it costs you $1 for one, or if it costs you $5 for one. So you've got M&Ms. One brand of M&Ms costs you $1 per M&M. Yes, I know that's exaggerated. Just go with it. And then another brand of off-brand M&Ms, your Walmart M&Ms or whatever, they cost maybe 75 cents per M&M. Would you rather pay $1 for one M&M, or would you rather pay 75 cents for one M&M? Me, I'd rather pay the 75 cents. So if the one costs 75 cents and then you've got 100 in the bag, well, you're just going to keep paying 75 cents for each of them. So if it's cheaper to buy one at 75 cents, it's definitely cheaper to buy all of them at 75 cents. So when you go to the grocery store, a lot of the times, or stores in general, a lot of stores will have this unit cost. That's what we're looking at here. It's called a unit cost. Cost per. A unit means one. So a unit cost is the cost per one of something, whether it's cost per pound, cost per gram, cost per M&M, cost per sheet of toilet paper. So a lot of grocery stores will have those when they have the sticker price. If you look at the small font below, you can see that, and then you don't have to do any math. But here's the thing. First of all, not all stores have that. Second of all, if an item is on sale, not all stores redo the unit cost, and they do that intentionally for shoppers like me, so they have to do the math. And third of all, what some stores, I noticed Walmart about 8 or 9 years ago was doing this, and I can't say if they're still doing it because I don't shop at Walmart, just for personal reasons. You do whatever you want to do, but Walmart's not the store for me. So back in the day, Walmart, being the clever people that they are, they would have the unit cost for brand A in one type of unit. They do it like the cost per pound. And then in brand B, they would do it like the cost per M&M. And the reason they did that was to confuse people and probably make them buy the more expensive item so that they can get their profits up. Now, again, I don't know if they're still doing this, but they definitely were in the past. And I'm not saying they did it for every single item on the shelf, but I noticed it for a couple things. And I don't even remember what it was. I feel like it was either toothpaste or toilet paper. I think it was a necessity. Toilet paper in particular, that's one of the more confusing ones to do because brands have different size squares. Some brands, brand A might have 400 sheets and brand B has 800 sheets, but brand B, they're half-size sheets, and brand A, they're full-size sheets. I think that's more normal for paper towels, but you get the idea. So you have to be careful with what you're comparing as well. If you're doing a cost per sheet, are the sheets the same size? Do they have the same effectiveness? I'm not saying you can't just base it on a factor like that. I'm saying you have to be careful. If you're comparing half size to full size sheets, just be careful. All right, so bulking on a budget. One of my favorite examples that I made up. And I used real numbers from a grocery store about a year ago when I made this problem. So you are trying to gain muscle mass. And one of the main ways to gain muscle mass is to increase your protein intake. Now you need to be lifting along with increasing your protein intake, but a lot of people will say if you just maintain the same, if you eat the same amount of protein and you start working out, you won't have as many, quote, gains as if you ate another 100 grams of protein every day or something like that. This is not a science class. We're not going to get into all the differences of whey protein powder versus soy protein powder and how one of these may or may not be as good for you as the other. Again, this is not science class. We're going to look at this strictly as an economic problem. Okay. So at your local grocery store, you find a whey protein powder that costs $20. So this is a jug. And inside of that jug, it has 32 grams of protein per serving. 32 grams of protein per serving and 12 servings total. So I did not tell you how many grams of protein are in the jug entirely. I told you that the nutrition thing says that there's 32 grams per serving and that there's 12 servings total in this jug. Okay, so that's thing one. We got a powder. Thing two, and by thing one and thing two, I'm not referring to parts of a ratio. I'm talking about completely different items here. So item two, there's some soy protein bars. Now, not all protein bars are soy. It's just this is one particular brand, and they're based off of soy protein. There are also whey protein bars. There's all sorts of other types of protein bars, but you find these. These are the first things you see, and they're $8. And inside of that packaging, each bar is 20 grams of protein. So it's 20 grams of protein per serving. So they're calling a serving a bar. And there's 6 bars individually wrapped. Now you might say, well, all right, so if I get the protein bars, that means when I eat one bar, I get 20 grams of protein. But if I get the powder, if I make one serving in milk and everything else, I'm going to get 32 grams of protein. And let's say water, because milk has extra protein. So first thing you're going, well, Mr. Beckner, I'm taking in different protein each day. If I do the jug, I'm getting 32 grams. If I do the bar, I'm getting 20. Let's just say that you were going to cut the powder down to 20 grams worth, so you were going to proportion it out. Or maybe you were going to eat like 1.5 soy bars. Either way, you're going to find your way to get the same protein each day. That's not the point of the problem. Point is, if all you care about is getting your protein as cheap as possible, which do you buy? Because you're going to go on this year-long regimen to just bulk. And you're going to take this diet super serious, which means you're going to have to go to the grocery store and buy 15 or 20 of these jugs, maybe 25 of these jugs every year. You're going to be buying, I don't even know, 60 different packages of these bars for the full year. So if you have to buy the same thing over and over and over and over and over and over and over, if one of them is a little cheaper to buy one, if you got to buy 60 of them or 30 of them, that savings is going to be multiplied out. So again, ignoring the types of proteins, ignoring how much we're actually taking in a serving at the time of consumption. Let's just do this cost analysis. So you want to keep the ratio of cost to grams of protein as low as possible. That's our unit cost. Unit cost is you take the total cost and divide it by either a weight or number of things. I wouldn't say it's a good idea to do number of things because one of these is a powder, one of these is a bar. You can't really divvy them up in such a way. The thing that we have that's consistent is grams of protein between them. So that's why we choose to do cost for the top and grams of protein in the bottom. That's going to be our unit cost. Now, you were given a total cost. You weren't given a cost per serving of either of these things. We were told the jug's 20, the bars are $8. So we were given a total cost, which means we're going to need to know the total amount of protein in each of these things. How much protein's in the jug? How much protein's in all 6 bars? We were not given that information, but we can find it. If we know the number of servings and we know the number of grams per serving, we can just do some math with those and hopefully it gives us the total. So that needs to be hidden. Just bump that down a little. So for the, and let's make sure I say the same thing, for the powder, and then for the bars. For the powder, the total protein should be equal to, what are the two things we're given? Why is that in green? That is weird. It's a weird default. For the powder, and we're only talking about the protein, it was 32 grams per serving with 12 servings. So serving 1 is 32 grams, serving 2 is 32 grams, serving 3 is 32 grams. There's 12 of those. So you could just add up 32 plus 32 plus 32 12 times, or you could use the idea of multiplication and say 32 times 12. Now, some people will just really quickly say 32 times 12, get their answer, and they're right this time, but let's lay our units out and make sure that everything makes sense. I've said before that when you do math with units, if you can get the units correct in the answer, that's probably the right way to do things. It's pretty rare otherwise. So let's take the 32 grams, and then that's 32 grams of protein per serving, per serving, per serving. Remember, after per goes in the bottom. That's about the 5th time I've said that today. We're finally getting to it. That's not a question mark, that's a colon. No, I'm sorry, that was an exclamation mark. There we go. So 32 grams per serving. A serving is a type of unit. 32 grams of protein per serving. Now let's take that times the 12 servings. Look at this. There's a serving in the bottom, there's a serving in the top. Those units cancel, and all we're doing is 32 times 12. And if you pull out your calculator, 32 times 12 is going to be 384. So that would be 384. The only units we're left with are grams. So that says that the total protein, I'm just going to do P for protein, is 384 grams in the powder. Does that make sense? Well, I'd hope so. If one serving is 32 and there's 12 servings, you should have at least 10 times that much. If you divided these, if you did 32 divided by 12 for some reason, you'd end up with 2.66. And if there's 32 grams in one serving, why would there only be 2.6 grams of protein in this whole jug? That would not make sense. For the love of math, after you get an answer, when we're dealing with problems that have relationships like this, ask yourself, does it make sense? If you're not doing that, you're going to get a lot of answers wrong that you shouldn't be getting wrong, probably. All right, for the bars, the total protein, and we'll do this in blue. The total protein, So the soy bars cost $8. We're not worried about the cost. We're just dealing with the protein. That's 20 grams per serving. So 20 grams per serving times the number of servings, which is 6 bars, 6 servings. So the servings cancel. 20 times 6 is 120. So there's only 120 grams of protein in the bars. Now again, your average Joe is going to walk in and say, oh, this thing costs 20, this thing costs 8. Give me the thing that costs 8 because that's cheaper. Now, maybe in the long run, maybe after buying 60 of those things, maybe that is cheaper still, but I don't know. That's what we're doing this for. We're doing the better approach. Instead of just saying buy the cheaper thing for one of them, we're saying buy the cheaper thing when you look at a unit cost. All right. So now let's get to the unit cost, where we take the cost and divide it by the grams of protein. So for the powder, the cost we said was $20. So $20. Then the protein, we said there was 384 grams. Now, the dollars in the top and the grams in the bottom don't cancel. Those are different units. So your answer is going to be in a cost per gram. And 20 divided by 384, I can't actually pull a calculator up this time. So we will 20 divided by 384 is 0.05208 blah, 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 blah. Now we're talking money, so we probably only go to the nearest cent, but I will warn you. I will warn you with cost analysis, sometimes going to the nearest cent isn't enough. If both of these things came to be 0.05, that means we would need to look at the nearest tenth of a cent. When you're talking about unit cost, sometimes the tenth of a cent or even the hundredth of a cent can be the determining factor. It won't be in this one. So I'm just going to write 0.05. So that's 5 cents or $0.05 per gram. That is the unit cost for the powder. For the bars, we said we were paying $8 for the box of bars, and in that we got 120 grams of protein per serving. So when we go to do 8 divided by 120, let's pull up our calculator again, clear the screen, 8 divided by 120, we end up with 0.066666. So that rounds to the nearest penny 7, so 7 cents. So 0.07. Now again, notice I'm not just writing 0.07. That's not what I'm writing as my answer. I'm writing all the units. The dollars and the grams do not cancel. Dollar symbol just goes in front instead of after, so it's 0.07 per gram, 7 cents a gram. Okay, so Bob goes in. Bob doesn't care about unit analysis. He looks at the $20 whey. He looks at the $8 soy, and he says, I'm buying the $8 because 8 is less than 20. But Jane, who plans on bulking for an entire year and says, well, I'm living on a budget. I need to make sure that my money is going to where it needs to be. So Jane decides to do this unit analysis and figures out that even though you're going to pay more for the individual jug, you get enough protein out of that jug to make it worth it in the long run, because 5 cents per gram is cheaper than 7 cents per gram. So the cheaper item is actually the powder. The powder. So what you could do is maybe say, all right, well, I need to be taking in 50 grams of protein a day. So that means you'd be eating 2.5 bars or taking about 1 and 3/4 of a scoop of protein, something like that. So if you needed 50 grams of protein per day, that's 0.05 cents per gram times the 50. That means you're paying $2.50 per day times 365. You're paying $9.12.50. I want to write that down. So say you need 50 grams per day. For the powder, that's your 0.05 per gram times 50 grams per day per, so in the bottom, and then there's 365 days in a year, so 365 days over years. So we're just doing 0.05 times 50 times 365, which is 912.50. Let's see, the grams cancel, the days cancel, so that's cost per year. Then if you do the bars, that's 0.07 per gram times your 50 grams per day times your 365 days per year. Grams are gone, days are gone, so you'll have a cost per year, and we're just taking 0.07 times 50 times 365, 0.07 times 50 times 365, and that's 1277.50. And that's per year. So guess what? That is a savings. You subtract, what was the other one? 912.50. That's a savings of $365. Now, admittedly, because we use the rounded 0.05 and 0.07 instead of 0.052 and 0.066666, this savings is slightly exaggerated. It's probably closer to like $320 or $310, but it still shows you that you're saving hundreds of dollars. So again, Bob thinks he's saving money because he's buying these $8 bars every time instead of the $20 jug. But if he does this for a whole year, enough protein to actually have an entire year's worth, that means Bob's going to end up spending about $350 more than Jane, who did the cost analysis. And Jane can take that $350 and then go spend it somewhere else. So again, you have some places that will put these unit cost analysis up. Some of them are inconsistent. Some of them aren't. Some of them, when they're on sale, they will still put the unit cost. Some of them won't. But if you got a cell phone in your pocket, you can just go and pull that out and divide two things and know for real. So this is a very handy tool to have in the real world to save you some money, maybe some really, really good money in the long run. You can do this for things like comparing your breads or milks. I mean, just your basic essentials, and end up saving hundreds of dollars over a year. Hold on one second. All right, so ignore the 3.4 for now. We're still in 3.3. We're not ready for that. So this is unit cost. This is a very, very powerful technique. I will guarantee you will see this on the midterm and on the final, at least one of them. You'll definitely have it in the homework as well. So be prepared for that. So let's go back to the initial idea of just looking at rates. Specifically, what we want to do in this guided activity coming up is we want to see how rates cancel when we've got fractions divided by fractions, things like that, or a fraction times another fraction. So we're going to go to page 133 on our guided worksheets. 133. All right, that thing I mentioned earlier where I was going to have to cut out for a couple of minutes is about to happen. All right, so give me a minute or two. All right, okay, we're good now. So for each question, determine the answer with proper units. The first one has been done with you. So this is just a bunch of problems, just straight up math, multiplications or divisions with things that have units. Some of these units have pers, not kitty cat pers, the word PER, which says the next thing goes in the bottom, per person in the bottom, per hour, hour in the bottom, per cubic inch, that means it goes in the bottom. So we got to make sure we can handle all these different types of fraction math. I won't do all of them, but I'm also not going to assign any of these as group work, but we'll do several of them. So number one's been done for us. We're taking $5,100 and dividing it by $300 per month. Now, I don't like that they put the dollar symbol after it. They should have used the word here. Me personally, symbol always goes in front of the number. So I just rather have this as 5,100 divided by either the dollar symbol in front of the 300 or say 300, and then the word spelled out, dollars per month. So the 5,100, you write your 5,100, then dividing by a fraction, and they skipped a step here. So divided by $300 per month. So the 300, the dollar symbol goes in the top, the month goes in the bottom. Now this 5,100 is written as a whole number. And you've got a whole number divided by a fraction. Some of you might not like that, so what you can do is you can write the 5,100 over 1. Whole numbers can always be written over 1. Never forget that. And we don't like dividing fractions. In fact, no math teacher has ever taught you how to divide a fraction. They tell you to instead multiply by the reciprocal. So this is $5,100 over 1 if you need to see it, times, so the red here will be showing the flipping. We have the month in the top, and with no number, you can just assume it's a 1 over the $300. It's not just the number that gets flipped, it's the units that get flipped as well. Please do not forget those. When you flip the number, you flip the unit. I didn't flip anything from the first fraction, just the one after the division. So check this out. You've got a dollars in a top, you've got a dollars in a bottom. Guess what they do? You're correct. They cancel. So you just got 5,100 divided by 300. Well, 51 divided by 3 is 17. The zeros cancel. So that's 17. The 1 in the bottom does nothing, but you have months in the top, so it's 17 months. So $5,100 divided by $300 per month is 17 months. So maybe this is saying, all right, Bob just lost his job because of coronavirus. Bob's got $5,100 in the bank, and he knows that he has to spend $300 per month just to get by on food, basic living expenses, whatever. And maybe Bob is wondering, how many months will this money last? Well, you can just play around with these numbers and symbols and multiply and divide them until you get something that's answered in months. So if you got $5,100 and you know it's going to cost you $300 a month to live, $300 per month to live, if you multiply them, you're going to get some big, ridiculous number, 5,100 times 300. Hold on. If you were to multiply them, so I'm going to show something wrong and then I'm going to erase it. 5,100, if you then just say times $300 per month, the 5,100 times the 300 is 1,530,000. And then you've got dollars times dollars, which is dollars squared. And then the month is in the bottom, so per month. What in the heck does that mean? Dollars, you have $1,530,000 squared per month. That makes no sense. Okay, so multiplying numbers didn't give us a number that made sense. Well, maybe divide them. Do the 5,100 divided by the 300 per month. Make sure the units are in place. We get an answer that's got appropriate units. We got a number that seems to make sense, $300 a month, 17 months. Yeah, that boils down to $5,100 total. Now, again, if you can't make sense of this, then you can't make sense of this. But if you are very consistent and always writing your units with your numbers, paying attention to the pers, knowing how to divide fractions by multiplying by the reciprocal, everything should work out pretty neatly. And that's just in the sense of you multiplying and dividing things willy-nilly, just trying to get an answer. And then if the answer makes sense, it's probably an appropriate answer. But if the units don't make sense, if the number doesn't make sense, you've probably done it wrong. There's none of that thought process here. They're just telling us what to do. So 400,000 people times 6.2 meters squared per person. Meters squared per person sounds kind of like a density of a population, like how much space each person has. So that's a times. So this is 400,000 people times 6.2 meters squared per, so fraction bar, person. Now people and person, different word, same unit. It's just plural and singular. So the people and persons cancel. You take your 400,000 times 6.2, which is 2,480,000, and then meters squared, because that's the only unit left over. Well, this looks like an area. So that is trying to say that 400,000 people would take up this much area if one person takes up this much area. 20 miles divided by 40 miles per hour. This sounds like Bob has 20 miles to drive, and he currently has a speed of 40 miles per hour. So 20 miles to go, 40 miles per hour. So I bet what we're going to find out is how long this takes. So, all right, Bob's got 20 miles to go down the road. He's going 40 miles an hour. How long will it take Bob? What do you do with the 20 and the 40? Do you multiply them? Well, if you play with the units, if the units come out as nonsense, that ain't what it is. Are you supposed to divide them? Are you supposed to do the 20 divided by the 40 or the 40 divided by the 20? Again, whichever one has the appropriate units would be the correct answer. Now, again, they didn't tell us to think that hard. They told us just take that and divide it by that. So we have our 20 miles, then our division symbol, and 40 miles per hour. So the 40 miles, that's our top, per hour. Don't cancel anything right now. Don't cancel with division. So this is 20 miles times, the hour is now in the top, and the 40 miles are now in the bottom. If you need a number up here, if there's never a number written, it's a 1. So the 20 is over a 1, that's a 1, boom. Well, look at this, the miles will cancel, gone, gone. You're doing 20 divided by 40, which is a half. The only units left over are hours. So that's a half an hour, whether you write it as that or 0.5, those are the answer, half or 0.5. So that says if Bob's got 20 miles to go and he's driving at 40 miles per hour, it's going to take him a half an hour to make that drive. Note, this is 30 minutes. I'm not asking for that answer, but you could convert from hours to minutes by multiplying by 60 over 1 or 1 over 60. Put the units in the appropriate place, make sure your units cancel, and everything will work out fine. I want to do one more of these wrong kind of things like I did up here, this little asterisk that made no sense. So again, real world, you are Bob. You have 20 miles to cover. You are driving 40 miles per hour, and you're wondering, how long is it going to be until I get there? And you're not sure what to do with these numbers. And maybe you don't do what we already have up here first. Maybe you do this. So again, this is going to be a nonsense thing, but maybe you choose to take the speed and divide it by the distance. So maybe you choose to take 40 miles per hour and divide it by 20 miles. Now that 20 miles doesn't have a per, so you got to write it over 1. So this would be 40 miles per hour, and then you're going to change it to times hour. Excuse me, I'm looking at the wrong thing. It was divided by 20 miles over 1, now it's times 1 over 20 miles. Now look at this, the miles still cancel, but the units are in the bottom. The 40 divided by the 20 is going to make a 2. So you get 2 over hours. Huh? 2 per hour. That's what that says, 2 per hour. That doesn't make sense. You're doing 2 per hour to what per hour? We're trying to figure out how long it's going to take us to get somewhere. 2 per hour is not a time. It's something per hour. It makes no sense. 2 miles per hour would be a speed. 2 per hour, again, I have no contemplation over that. So if you did this with your units and everything, you go 2 per hour, that makes no sense. Maybe try multiplying, or maybe try dividing this way. Oh, I got an answer with hours. That's probably what it should be. Again, this concept of dimensional analysis, just out with the old, in with the new, and or multiplying by units and canceling appropriately to get a unit that you expect to have. Those two ideas paired together open up an entire world of mathematics under assumptions. Again, math on the back of a napkin, as they call it. All right, next one, 450 pounds divided by 50 pounds per cubic inch. 50 pounds per cubic inch. So this is kind of like a weight distribution. And this says, all right, we got 450 pounds total. Maybe we're looking for how much volume we need, how many cubic inches we need. So we got 450 pounds divided by the 50 pounds per, so fraction, cubic inch. Well, this is 450 pounds times then we flip. So now it's cubic inches over the 50 pounds. 50 will go into 450 9 times. So that would be 9. The pounds cancel. All we have left over is cubic inches, and they're in the top, so it's 9 cubic inches. So if it's 50 pounds per cubic inch, so 50 pounds per cubic inch of volume, that says if you've got 450 pounds of stuff, that means you need 9 cubic inches of volume. Let's skip to 7. So I got to clear my screen. Let's skip to 7. We'll do one last one. All right, so we got 210 miles divided by 30 miles per gallon times $2.50 per gallon. Man, this sounds like some real world stuff right here. This sounds like Bob drove 210 miles. Bob gets 30 miles to the gallon in his car consistently, and gas at the pump is $2.50 a gallon. Now, right now, if you're buying the low grade gas, 87 whatever octane, we're looking at like $1.80, but that's just right now. That'll change. That's going to go up sooner than later. Again. So these are just numbers in a problem. But this, all right, Bob drove 210 miles. Bob always gets 30 miles per gallon in his car every single time without question. That's not going to happen to you ever. Your miles per gallon is going to vary whether you're on the highway, whether you're in town, whether you're hammering on the accelerator, whether you're coasting to your red lights. Things like that will affect your fuel efficiency. But again, point of the problem, Bob, at least this one time, 210 miles, he knows he gets 30 miles to the gallon, and he knows he's paying $2.50 a gallon. It sounds like Bob is wondering how much he's going to pay at the pump. So let's write everything out appropriately. We got 210 miles divided by 30 miles per gallon. That's a per, so that's a fraction. So this is miles per gallon, and then this whole thing gets times by $2.50 per gallon. So 250 over gallons per gallon, so over gallon. Now this thing in the front, this is a excuse me, this is called a compound fraction or a complex fraction. 2 words, same meaning. Compound or complex fraction. I like to call them compound because complex has a deeper meaning in math. This just means a fraction inside of a fraction. It's like inception. So what we have to do is clean this up. This division bar right here, this big division bar, this one right here, let's change that to the old school division symbol. So this will be 210 miles, then the division symbol, then the thing in the bottom, 30 miles over gallons, then times your $2.50 per gallon. Now, what we will do is we will flip the fraction with the old school division symbol in front of it. If you have the ability to go straight from having the compound fraction to what I'm about to write, be my guest. Most, if not all of you, though, probably need to do it this way. Just trust me. So 210 miles will now go times gallons over 30 miles, and then times our $2.50 per gallon. Now let's see what's going to cancel. What's going to cancel? We got a miles in the top and a miles in the bottom, gone. We got a gallons in the top, gallons in the bottom, gone. The only unit left over is this dollar symbol. So the answer is going to be in dollars. We just got to take the 210 divided by 30, which would be 7. And then we got to multiply it by the $2.50, and you get $17.50. So again, kind of the real world association here, if Bob drove, he put 210 miles on his odometer. 30 miles per gallon is just his known average fuel consumption. Trying to write really small. Known average fuel consumption, known average fuel consumption. And then $2.50 per gallon, that's the price at the pump. Price per at the pump. So that means Bob is going to pay $17.50. In the real world, no one knows their fuel consumption to the decimal place. You would be able to do a similar calculation, though, and figure that out. So if you knew that you drove 210 miles, if you knew that you paid $2.50 per gallon, and you knew that you ended up having a total cost of $17.50, you could multiply and divide these numbers and ultimately get your 30 miles per gallon average fuel consumption, as long as you can get an answer that has miles in the top and gallons in the bottom. But the thing is, you can't be afraid. You can't be scared to just multiply and divide things and write units out. Because if you sit there and you don't do anything, you're not going to get anything done. You have to try, and you have to fail, and you have to try, and you have to fail, and then you have to try. Oh man, I got it right, sweet. You're going to have those light bulb moments, and it's going to feel really good, and it's going to feel painful when you get it wrong, but you can't sit there and do nothing. You can't just stare in outer space. Write things down, write the numbers, write the units, multiply, divide. That's how you can get things done in the real world. All right, 10 o'clock. I got 15 more minutes. I mentioned earlier, in case you came in a little after, that I have to cut class slightly early today due to an appointment related to having to cancel class last time. We're good on that. So clear screen. Let's go off of annotate, please, and thank you. Back to the notes. Dosage and concentration. Specifically dosage, all that stuff I was just talking about, multiplying and dividing numbers to just get an answer that has appropriate units, this is the concept of dosage. The concept of dosage is centered around multiplying and or dividing a bunch of units, a bunch of numbers, units and or rates, until you get an answer that has appropriate units. This should be the answer. That's everything I was just talking about. So your fuel consumption problem in the real world, when you're, okay, I know I paid $17.50 at the pump. I know I drove 210 miles. I know the gas cost me $2.50, et cetera, et cetera. Just multiplying or dividing those numbers with those units in place and ultimately getting an answer that has the units, what you would expect for that type of quantity, that would be the accurate answer. There's a whole field of mathematics devoted to that. We will not be doing true dosage problems in this class together. If I had an extra semester, or at least an extra 2 or 3 weeks worth of time with y'all, then we could get into this dosage stuff. Admittedly, all of the dosage problems that our textbook goes into are over our heads. I'm even okay admitting this in a recorded lecture. When I went to the training session for these QR courses a couple years ago, because this was like a brand new type of math for us to teach. It's not just algebra where all the teachers know this stuff. There were some things that teachers had to learn, like Excel and honestly how to approach this and how to handle these guided worksheets, blah, 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 blah. But so when I went to the training sessions for this, there were teachers in that training session, there were math teachers in that training session that couldn't handle the dosage problems. So if a teacher can't handle it, I have a hard time giving it to my students, if you get what I'm saying. Now, the teacher in front of you can handle them, but that just doesn't mean because I can do it, y'all can. I really kind of I don't want to hold y'all to a higher standard than colleagues. Don't think that's fair in the world of math. So this is one of the topics that I trim out. So in this section, I'm not saying we're going to skip this section because there's another half of the title. There's even a arguable third title that would go in here, and that's density, but density is quite literally a concentration. Just a different type of concentration. So again, dosages, we're not really going to get into, oh, okay, Dilantin at 0.5 grams per dose is ordered and isn't available at 15 milligrams per 3 milliliters. Compute how many need to be administered to a person weighing this much or this size or anything. Again, you just multiply and divide the numbers and the units until you get the unit of the answer you're supposed to have. So if the answer is supposed to be a weight, you're looking for pounds. If the answer is supposed to be like a grams per milliliter, then you're trying to multiply and divide things so that that happens. And you can use the idea of out with the old, in with the new to try and force that. And sometimes you do it wrong, and then you start over and you just make another choice. Guess what? When I do dosage problems, I do it wrong 2 or 3 times before getting it right on the really complicated ones, as do all people. Okay, so we're going to focus more on the idea of a concentration, and I don't want to reveal too much. So this is one of my favorite problems to tease students with, and by tease I mean I talk about M&Ms and bringing them to class, but when we're in class I don't actually bring them. So each one of y'all needs to go and buy a bag of M&Ms before next class and just do this on your own if you want. And imagine there's other people with you. But I'm not going to buy you M&Ms. I don't buy candy for people. I'm mean and evil because I don't buy candy for people. Okay, so example. A teacher, and without really going into the idea of concentrations and what it means, we're just going to lead by an example to try and get this concept. So me, a teacher, in theory, brings a bag of M&Ms to class, and in this bag, there's 50 pieces in the bag. And he or she, he because it's me, will distribute them to 5 students before class. So it's before class, you know, maybe there's 20, 25, 30 students in class, but it's 5 minutes before, so there's only 5 people there. And I say, all right, for being early, I'm going to give you all some candy, but you got to tell me how much candy do you each get? So that question is, what is the ratio of pieces of candy to each student? So the rate we're doing is pieces to students. So there's 50 pieces to 5 students. 50 divided by 5 is 10. So that says it's 10 pieces of candy per student, because students in the bottom, no units cancel here. Then any unit in the bottom gets a per. So 10 pieces per student. So student A, 10 M&Ms. Student B, 10 M&Ms. Student C, 10 M&Ms. Student D, 10 M&Ms. Student E, 10 M&Ms. All 50. Teacher gets none. Teacher doesn't want them. What's wrong with your teacher? Doesn't want candy. Okay, so all of this is in theory, and I'm having my students do the math. And unfortunately, while my students are doing the math, it was only like 2 minutes before class. And in that time, a whole bunch more students come in. So by the time these students have done their math, and I haven't even opened the bag of M&Ms yet, or I haven't distributed them, because all these other students have come in, well, I can't just give those 5 students candy. So 20 more students show up just on the drop of a dime. It's now time, and 20 more students just march in. And I go, oh darn, we finished the math, but I haven't given out the candy, so I got to redistribute. I can't just give 5 students candy. That's not fair. And the joke was originally, I hope you didn't eat any. I haven't distributed yet, so I need to delete the joke for how I've said it. Now, how many does each student get? And then there's a couple of more questions that I'll focus on later. I'll go and read them once. If you multiply the number of students and number of candies, so this is just us blindly saying, hey, multiply this thing and this thing, what's the answer? Is this consistent? So let's hold on to that for just a bit. And let's just deal with this part. So, 20 more students show up and I gotta redistribute the candy to be fair. How many does each student get? So again, we're looking at the rate of pieces of candy to students. So again, pieces per student. We still have 50 pieces of candy total. But now instead of 5 students, I'm going to make a mistake. I'm making 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 a mistake. Is it 20 students in the classroom? So I would love for us to be in the room together, and then someone raises their hand really quickly and says, no, sir, or no, Mr. Becknor, or no, Rodney. That's 20 more students show up. There was 5 originally. If 20 more show up, that means there's 25 students in total. So be careful. There's always little subtle details that can be thrown at you like that to make your math wrong. 50 divided by 25 is 2. So now it's just a measly 2 pieces of M&Ms of candy, whatever, per student. I mean, hey, at least you're still getting something, but you know those 5 people that were going to get 10 M&Ms are a little peeved. Okay, this 10 pieces per student and 2 pieces per student, these are what we call concentrations. Concentration is a rate. As you'll see down here, concentration is a rate of blah, 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 blah. But hold on, before we get to the official definition, we got a couple more questions. But that's what concentration means. It's a something per something. It's a rate. And it doesn't have to be pieces of candy per student. This could be something much more complex. It could be grams per milliliter, like in a dosage of medicine or something like that. It could be people per square mile, like we kind of referenced earlier. I think we said meter, but you get the idea. So that's a concentration of people in comparison to land or space. Concentrations are rates. All right, so if you multiply the number of students and the number of candies each student gets, again, the number per student right here, this number of candies each student gets is the number per. What is the answer in this? Is this consistent? So they're asking us to do this twice. They're asking us to do this for the scenario where 5 people got a lot and the scenario where 10 people got, where 25 people got a little. So for scenario A, what are we doing? We're multiplying the number of students for both of these times the number of candies each student gets, which was the pieces per student. Pieces per student. That's what we're doing. So for scenario A, the number of students, we had 5 students. So it's 5 students. And we're going to multiply that by the pieces per student, which was 10 pieces per student. So 10 pieces per student. The students cancel. 5 times 10 is 50, so we get 50 pieces. Does 50 sound familiar? It should. It was the total originally. All right, well, let's do this for scenario B, which had 25 students in total. We're going to multiply by its concentration, which we didn't have to give it the name, but the number of candies per student, which was 2 pieces per student. The students will cancel again. 25 times 2 is, guess what? 50, and you're only left with pieces. The same answer. It's consistent. Also, the 50 pieces and the 50 pieces, that was the total. So what's going on here? What does this do for us? It gives us what they call in the worksheets a clever equation. I only use the clever in quotes because that's how the worksheets refer to it, but it gives us the concentration equation, which is this thing below. So this whole idea of a pieces of candy per student is a concentration. But when you're dealing with the real world, our concentrations are a little more convoluted. It's usually like grams per milliliter or feet per cube, things like that. It's just too much more convoluted things that you might have a more difficult time wrapping your head around. So it gives us this concentrations, which are a rate of an amount per unit of volume. Now, I didn't have volumes above, so per unit of volume, we were calling the students the volume. So the volume was the students in that past example. The volume was the students. So if you ever take a concentration times the amount of volume, so in the previous one we were doing the candy number of candy per times the number of candy, times the number of students. The number of candy per student times the number of students should always give the total amount of the substance. It was total M&Ms, but in general, we're talking liquids, solids, gases when we're dealing with real world problems. If you only change the volume, if you only change the number of people, there should be just as much substance in it, which means the concentration has to change. So we changed the volume of people in that previous example, which changed the concentration. When we increased the volume, the concentration dropped. When we went from 5 students to 25 students, when we increased the volume, we increased the students from 5 to 25, the concentration went down because the total amount of what we have to distribute doesn't change. When you have to distribute it to more people or to more volume, that weakens the concentration or it lowers the amount of candy that you can give out. So this is a very unique equation that quite honestly we don't ever see in any more sections of this course, but it is important. If you take one scenario, its concentration times its volume, it should be equivalent to another scenario's concentration times its volume. So maybe you know 3 of these 4 quantities. Maybe you know situation 1 entirely, but situation 2, you're missing either the concentration or the volume. You can plug them in and solve this. This is similar to a proportion, but it's not fraction equal to a fraction. It's a product equal to a product. And this is not a proportion. Concentrations are not proportions. They are actually inversely proportional, which means you can't set it up as fraction equal fraction. So again, this is a very specific setup. Now we are out of time. So next class, when we start out, we'll do a worksheet that is very, very, very heavily related to this. Then we'll talk about density, and that'll finish up 3.4 for us. So I do need to go ahead and call it a day. So due dates, today is the 18th, so we need to erase some things. 3.1 is due. We've now talked about 3.2 and 3.3, so 3.2 and 3.3 will be due a week from today, which is the 25th. Our next Excel occurrency was due 6/23. That was Tuesday. The next one is 3.1. I'm sorry, 6/23 is not today. Good Lord, what am I talking about? I'm looking at the 16th. I don't know what happened. I don't know why I said that. The next Excel that is due is your currency, and that's due on Tuesday the 23rd. There we go. Project's still up. The discussion board, oh shoot, what pages were they? I was hoping to have this typed already. It was the second one was page 126. And it was, we did Mercury, Venus, and Earth. So you had to do Mars, the asteroids, all the way up to Neptune. There were 6 opportunities for that one. Then for the other one, it was page 121. And it was numbers 3 and 4. That was 4 opportunities. And again, I say 4 and 6 for a total of 10, but if someone does something wrong and someone then comes in and gives the right way, there's an 11th opportunity. Or maybe someone does something right, you think it's wrong, and you type up your explanation. Again, I'd still count that as a participation point. It sucks that something was right and you have it wrong, but it's still discussion. Don't do it intentionally. And if that happens, I would love for someone else to come in and say, hey, I think the first person was right. Or if there's someone does it wrong and then someone does it right, maybe someone else comes in and says, I think the third person did it right. Alrighty. Quiz. Your next quiz will be posted in Canvas by 5 p.m. today. It will be due Tuesday. I think someone just left at the worst possible time, on the 23rd. I'm not saying what the quiz is, but it'll be posted in Canvas by 5 p.m. today. So look for that. But I'm about to run to my appointment, then I have to teach another class, so I'll get that set up after. Have a good one. Please email me if you have any questions. Sorry, I was a little scattered at the beginning. Like I said, I'm not feeling perfect. And hopefully everything will be back to normal on Tuesday. Again, email me if you have any questions. And we're going to start talking about the midterm coming up soon, because that'll be covering up to chapter 4, and we're about to start chapter 4. Have a good one.